morning, everybody. Hope you're all healthy and safe at home. So, let us continue with our section 9.8 line integrals. So, in the previous class, we had discussed the formulas how to calculate the line integral of a given function along a curve. Okay, and we had three types of line integral. That is, we had to find the line integral with respect to x, with respect to y, and with respect to the arc length of that curve. Also, we had different methods to calculate this line integral. That was one was when the curve was defined parametrically, and the curve was defined by an explicit function. So in both the cases, we had discussed the formulas to calculate the same. So we will begin this section by considering another example which is given in your textbook. This is example 4 that is regarding the concept of splitting or dividing the curve into more than one smooth curves. That is, we had also noted in the previous class that if we are considering any smooth curve, and if we can partition that smooth curve into further smooth curves, say C1, C2, etc., then the integral of that along that curve will be integral along each smooth curves that we are considering. So let us see an example. Here in example 4, we are asked to evaluate integral over C. The C is a closed curve, y square dx minus x square dy on the closed curve C, which is given in figure 9.86e. So you can see the figure is of this form. The curve is going in this manner. So just keep in mind the orientation also. It is important, the direction. So this is our closed curve. So first what we do is, we can see that this whole curve C consists of we can consider it as three different curves, right? We can consider this one as C1, C2 and C3. So to find the integral along C, what we'll do, we will find the integral along C1, along C2 and along C3 and sum all these three together. Okay, now note one thing, C is closed, but if you take individual smooth curves C1, C2, C3, they are not closed, right? C1, C2 and C3, they are not individually closed. So you can see. Now let us see, we'll consider each curve individually. So first let us consider C1. Okay, C1 is varying from, so in this you can see that there is a variation or there is a change in x, not in y. Y is remaining constant, right? Here y is equal to 0. So in C1 y is 0. So when y is 0, what will be dy? Dy will be again 0, and x is varying from 0 to 2. Is it clear from the figure? There is a variation of x from 0 to 2. So we will replace this integral by integral over C1 y square dx minus x square dy will be equal to, there is variation in x only, not in y. So 0 to 2, and what is y? Y is 0. 0 into dx minus x square into dy is again 0. So altogether this integral will be 0. Now let us consider second curve, C2. In C2, you can see that there is a change in y, right? X is remaining constant, but what is x? X is equal to 2. So if x is 2, what will be the value of dx? Dx will be 0. And what is the variation of y? Y is varying from 0 to 4. So let us calculate the integral over C2. Integral over C2 y square dx minus x square dy will be equal to integral from 0 to 4. Y square remains as it is, but dx is 0. So y square into 0 minus x is 2. So x square is 4. 4 into dy. That is integral 0 to 4 minus 4 dy. What will that value be? That will be equal to minus 16. So now finally we'll consider the curve C3. In the curve C3, you can see that there is both variation of x and y, and also it is the value is like it is the curve of a parabola y is equal to x square, right? It's clear from the figure. Also, you can note the points when x is 2, y value is 4. So that is xy is equal to x square. So what we are going to do is from this we are replacing y by x square. So we'll just consider the variation of x. So here again x varies from 0 to 2. So integral over c3 y square dx minus x square dy will be equal to 0 to 2. Y square is y is x square, so y square will be x raised to 4. X raised to 4 dx minus x square into what will be dy when y is x square? 2x dx minus x square into 2x dx. So altogether it will be integral 0 to 2 x raised to 4 minus 2x cube dx. So when integrating, you will get the value is equal to 8 by 5. So what will be the actual integral over c? It will be the sum of these three values. That is, on c1 we had 0, c2 we had minus 16, and on c3 we had 8 by 5. So the sum will be, or the integral, required integral will be integral over c, y square dx minus x square dy will be equal to 0 minus 16 plus 8 by 5, which is equal to minus 72 by 5. So the negative sign must be because we had not considered the orientation, or if we are considering any one point, if we had used here the curve is moving downwards, or C3 is an arrow is pointing downwards. So here if we had used negative, we'll get the correct value to be minus 72 by 5. So now I'll just make a note of one thing, that is if you are considering, can you just look at figure 9.8.7, you can see two curves, okay, but they have different orientation, okay. In first curve it is going from A to B, whereas in the second curve it is moving from minus B to A. So if but if one is C, the other is the negative of C, right? So we can say that it is important to be aware that a line integral is independent of the parameterization of the curve, provided C is given the same orientation by all sets of parametric equations defining the curve. That is, it is just, we know for definite integrals, we know that integral a to b f of x dx is equal to minus integral b to a f of x dx. Okay, integral if you are choosing integral a to b f of x dx, that is minus of integral b to a f of x dx, the limit will be changed. So here also we have integral minus c p of x comma y dx plus q of x comma y dy will be equal to minus of integral over c, okay, p dx plus q dy. I hope the concept is clear. So just have to remember. So for example, if we had considered in the first part of example 1, integral over c, we had to calculate xy square dx. We had got a negative value. So if what will be integral over minus c, it will be nothing other than minus of minus 64, that is 64. Okay, so if we are given integral over c, to calculate integral over minus c, we just have to multiply it by negative 1. Okay, if suppose integral over c p dx plus q dy is some k, then integral over minus c p dx plus q dy will be equal to minus k. So I hope that concept is clear for you. So now what we'll do is we will move on to the line integrals in space. Okay, space curve, that is, we are last class we had discussed about line integrals in a plane. So here in this section we will discuss about the line integrals in space. So it is very much similar to the concept of line integrals in plane, except that we will have, instead of gxy, we have gxyz. Okay, so you can see the formulas. The line integral of a space curve c with respect to x will be given by integral over c g of x, y, z dx is equal to limit norm p tends to 0 summation k equal to 1 to n g of xk star, yk star, zk star into delta xk. Same as that of line integral in plane, except that there is one extra variable z in here. Similarly, line integral of c with respect to y will be integral over c g of x comma y comma z dy is equal to limit norm p tends to 0 summation k equal to 1 to n g of xk star, yk star, zk star into delta yk. And line integral of c with respect to z, this is one extra formula which we will be having in case of line integrals in space, because we have to consider the line integral with respect to z also. So integral over c g of x, y, z dz will be equal to limit norm p tends to 0 summation k equal to 1 to n g of xk star, yk star, zk star into delta zk. And here also we will have line integral of c with respect to the arc length, that is integral over c g of x, y, z ds will be equal to limit norm p tends to 0 summation k equal to 1 to n g of xk star, yk star, zk star into delta sk. So it is very much similar to the line integrals in plane. And even in the last section we had seen formulas to calculate the line integral with respect to x, y and z. And if you remember, we did not use this limiting formula, we had used a different formula depending on the definition of the curve. So even in this case, when the line integrals in space we are considering, here also we can use the same formulas. We can see that if the curve is defined by the parameters, that is the curve is defined parametrically, if c is defined by x is equal to f of t, y equal to g of t and z is equal to h of t, where t varies from a to b, then what will be integral over cg of x, y, z dx. What we have to do, we have to replace x, y, z and dx everything in terms of t. So that will be equal to integral a to b g of f of t comma g of t comma h of t into f dash of t dt. And integral over c g of x, y, z dy will be integral a to b g of f of t comma g of t comma h of t into g dash of t into d of t. And integral over c g of x, y, z into dz will be equal to g of f of t comma g of t comma h of t into h dash of t dt. And the line integral with respect to the arc length, that is integral over c g of x, y, z ds will be equal to integral over a to b g of f of t comma g of t comma h of t into root of f dash of t square plus g dash of t square plus h dash of t square into dt. So this is how we can find the line integral of curves in space. So let us see an example which is given in your textbook. The example to calculate the line integral on a curve. So we are given the curve C is given by, it is the helix, x is equal to 2 cos t, y is equal to 2 sin t and z is equal to t. So and the variation of t is given to be from 0 to 2 pi. So what will we do? We will replace everything in terms of t. So if x is 2 cos t, what will be dx? It will be minus 2 sin t. And if y is 2 sin t, what will be dz? Dy will be 2 cos t. And if z is equal to 2 or z is equal to t, what will be dz? Dz will be dt. So using all these we will substitute, and integral over c y dx plus x dy plus z dz will be equal to integral 0 to 2 pi y is 2 sin t into dx is again what it is minus 2 sin t. So altogether we get minus 4 sin square t. So minus 4 sin square t plus 4 cos square t plus t into dt, right? And we'll use the formula integral over c p dx plus q dx will be equal to p plus q into dx. So you can do it. Now here you can take 4 common by taking out 4 common, sin square t plus cos square t. Sorry, it's not plus, it is cos square t minus sin square t. So that will be the formula, trigonometric identity, that will be of cos 2t. So it will be integral 0 to 2 pi 4 cos 2t plus t dt. So what will be the integration? Integration of cos 2t is sin 2t by 2. So it will be 2 sin 2t plus t square by 2, varying from 0 to 2 pi. Now sin 2 pi is 0. So it will be 2 pi square by 2, that is 4 pi square by 2, that is 2 pi square. And when t is 0, again sin 0 is 0, and when t is 0 you will get 0. So that is how we can calculate the line integral of a curve in given 3 space. We just have to transform or use the parameters given to us and solve correspondingly. So that's it. That is it for today's section. We'll discuss more about the work done and the application in the next class. So thank you. Stay home and stay safe.